You can I'll just quickly repeat these things. Sorry for that. I forgot to uh, start the recording. Welcome all of you for today's session, week 5 live session for economic operations and control of power system. We're following the same agenda. Uh, it's a reminder that deadline for assignment 5 is August 28th and for assignment 6 it is September 4th. And you can find the recordings on this link, which is available on portal as well. We were talking about the week 5 overview, and in week 4 we have discussed priority list method and dynamic programming. Week 5 deals with this Lagrange relaxation method. So first we will see what is the in week 5 all these things were discussed: unit commitment using Lagrange relaxation, hydrothermal scheduling, economic dispatch with limited energy supply, and then recap of AC power flow. Also, when that recap of composite uh, characteristics, that fuel characteristics, incremental fuel or cost characteristics for several generators. If we have several generators, we can get one single characteristics. That also we have seen in week 2, I think, composite cost curve. That was also discussed. So these two topics are recap. So moving on to that Lagrange relaxation, we were talking about the what is the motivation for using Lagrange relaxation? The motivation is to decompose a very big problem which may not even be solvable by the solvers. The problem may be difficult. And another thing is, one thing is we want to solve it. We should computationally, it should be tractable. We should be able to find a solution. Finding a solution is important, but another thing is that we should be able to do that, find a solution as quickly as possible. And this is very important when we are doing this, dealing with operational problems, such as unit commitment. For planning problem, although time doesn't matter because we are planning for 10 years, even if the problem takes, let's say, 5 days to solve, we can wait for that. But it's always good if we can reduce the time because, let's say, something we solved the problem, we formulated the problem, we solved it. It took 5 days, but after when the solution, when it was solved, if we found that there was some mistake, results were not as expected, and it can be due to several steps. It can be due to a problem with data, input data. It it might even happen that after 5 days, it is not converging. So it becomes intractable, not converging. It can happen that after 5 days, when it is solved, you see the solution is very far away from expectation. Then we need to change things, check, debug it, and again run it and wait for 5 days. And sometimes even we have to change the data set, do several iterations with different data set. Even we want to do sensitivity analysis, that if there is a small change in data, because All these planning problem we are solving for a future time frame, 10 years ahead. We don't know what is going to happen. There is always uncertainty associated with that. Nothing is known a priori. We are just projecting, even the load is not known. We are simply based upon the historical profile, we are forecasting it, and it might come out to be different. So whenever we are solving any such problem, we always want to do sensitivity analysis. If there is a small change, maybe 10%, 5% change in the input data, load data, or cost data of these plants, battery, then how the solution is going to be affected. And if the solution takes 5 days, then for each run, each change in the input, it will take months. So it's always imperative to have less solution time. And for that purpose, we are here. The motivation for using these different methods is we want to decompose the original problem so that we can solve it quickly. Original problem might not be one is it might not even be solvable. This second, it might be taking more time. We want to deal with all both these problems. So we want to first we are decomposing that original problem into several sub problems which are smaller, which can be solved very quickly, and also they are easier. So that is the motivation for using these different methods. And Lagrange relaxation is one of such method for decomposition. Okay, so in power system, we need decomposition. This I have already mentioned. Why do we need decomposition and why are we talking about decomposition in power system? Because we want to solve the problem and that too uh, within less time. We want quick solution within time frame. Especially it's very important for operational problems where we want a quick solution. We want to make certain decisions, and if the solution time is more than that window which is there to make decision, that if entire that window is spanned by the solution itself, then it's of no use, because this was supposed to, let's say that decision was supposed to be made within 30 minutes and the solution time itself is 35 minutes, then what's the use? It's of no use for us. So that's why it's very important. So these are different methods. So those problems which have decomposable structure, these are of two types. One thing, one can be there, and this operational problem falls in this first category, where we have a complicating constraint. As we have seen, we'll see also the loading constraint or the power balance constraint is the one which is linking all the generators. All the generators, even there is a coupling of time and generators. So this loading constraint where the demand is to be met for each hour, it complicates the problem. If it was not there, we could have easily solved that problem for each generator individually, it for each time period. So we have only a small problem and we can easily solve it. But this constraint makes it difficult. Similarly, another type of problem is complicating variable, and planning problems generally fall in this category. Because what happens, these variables are discrete, generally discrete variable. It can be continuous also. If you want discrete, it becomes when suppose we if roots have. call them.
Hello, sir, your voice is not clear. Hello. Hello. Hello.
Hello.
Ah, sir.
Sorry, I think there was a network issue from my side. The call got
Okay.
dropped. I'll share the screen again. I don't know where did uh, what was the last thing which you heard?
Sir,
Yeah.
your this one only, sir. Okay.
This one?
Yes, sir. Planning problem.
Yeah, so planning problem I was saying, the planning problem falls under this category where we have a variable that complicates the problem. If that variable is removed, then it becomes we can solve that problem for each year or even each day separately. And that variable is, let's say we want to plan for transmission lines. Then we have some possible right of ways for transmission line that we can have 5 transmission line between so and so buses. And out of these 5, I want to know which of these 5, all the 5s are required or 4 or 3. So these are discrete variables, either 1 or 0. So we have 5 values. If it is 1, then it has to be, if a transmission line is to be connected, then all the constraints need to be satisfied. If it is not there, then those constraints are not required. So this variable, whether transmission line should be erected, constructed or not, it complicates the problem. It links the problem. It couples the problem over time. Similarly, this constraint is also doing the same thing. It is coupling the generation, the output of the generator over time and over generators also, because we want to satisfy the sum of generation has to be equal to the load for each time. So one output of one generator is affecting the satisfaction of this constraint. So if this constraint is not there, then it's easy to solve. But this constraint is making the problem difficult. Here variables are making the problem complicated. That's why they are called complicating variable and complicating constraints. So for complicating variables, we have this method Bender's decomposition. And for complicating constraints, we have all these different methods, Lagrange relaxation. Then these two are augmented Lagrange relaxation methods. And then this is one more. We in this course we have only discussed about this Lagrange relaxation. So here the constraint is the problem which we discuss is the complicating constraint here is loading constraint. Even we didn't consider this ramping constraint in the formulation, but that can also be considered. And this will also another constraint which is complicating the problem. These are the constraints which are, if that's why we will see why it's called a relaxation. So this is the problem, right? You want to minimize the cost of generation plus startup cost. And this is multiplied by u because it's a binary variable. We don't know whether the generator is to be turned on or off. It's either 0 or 1. So only when it is on, the startup cost should be added and this production cost will be added. Otherwise, it should not be added. That's why it is multiplied here. Then it is subject to these constraints. One is loading constraint, or this is also the power balance constraint. And this is to be satisfied for each time block, for each t belonging to t. Similarly, this technical limit, this is also for each generator. I belongs to Ng, that's N, and T belongs to T. And by the Lagrangian function, we can move this. We have already seen this in economic dispatch also. Move it to objective function. So this is, we are adding this loading constant here. It is Lagrange multiplier or dual variable lambda t. For each time we have this constraint. And now if we see this term, this is independent for each generator. Right? And similarly, these two can be separately done. For each generator, this can be satisfied and this cost can also be found if this term is relaxed. If this term is not there. Because this is the term which is relating generator, the output of one generator with output of other generators. If it is not there, then you can independently solve the problem for each of the generators. But we cannot even avoid this because we want to meet the power balance condition also. That is why it becomes a iterative and a two-step process. In one step, we decompose the problem into smaller problems without considering this or relaxing this constraint. That's why it is called relaxation, because we are solving the problem in one step by temporarily relaxing this complicating constraint, which is here the power balance constraint. We relax it and then we solve the problem. We are relaxing it for time being and then again updating. That's why it is called a relaxation. I hope it's clear why it's called relaxation.
Yes.
This is same. Yeah, same thing is written again here, that these two, this cost function together with these constant, they are separable over units. Independently, they can be solved. That means one generator, the output of one generator does not affect the other generator with respect to the cost as well as this technical limit constraint. However, this constraint, this loading constraint, it links the problem over the units across the unit. Therefore, the generation of one unit affects the other. And that affects the satisfaction of that load generation balance. Therefore, it is solved by relaxing this loading constraint as if they did not exist. And for this, we use this dual optimization procedure. In this, we have this dual procedure. We maximize this Q, this Lagrange function, with respect to Lagrange multiplier and minimize them with respect to these variables. Here you can see this is the same Lagrange function which we have written here. This first it is minimized with respect to this p and u variables and then maximized using over this Lagrange multiplier. This is a dual form. Primal form will be opposite. The dual form is this max min max with respect to lambda and with respect to field. And primal is min max. Okay, so what we are doing here, first step we are this one is the maximization step. Here we are updating the lambda. What should be the new lambda? If we have a function this in terms of lambda, maybe some lambda star 2 plus 2 lambda plus 1, and we want to maximize this function with respect to lambda, then we can differentiate it and put it equals to 0. And we have seen that we can do that. We can find out the lambda. Yes, if we have this, it's a non-linear function, right? And we want to maximize. We want to find this value. And if we start with some initial, all the nonlinear functions, we need to provide initial guess. So if we start here, then we should finally reach up to here. For that, we update the initial value. This is our initial guess. Generally, we take it as 0. So if we start with 0, we have to reach here. If it is 0, then we need to reach this lambda star, which is the which results in maximum of this Q lambda. This we are doing using this gradient search. We are updating this. This is the search, and dq by d lambda is same here. You see, this is Q lambda. If we differentiate this with respect to lambda, this is not dependent on lambda. With respect to lambda, it's constant. Only this thing is left. With respect to lambda differentiation, we will get this. And we can calculate and update the lambda value by using this alpha. Second step is once we have a lambda which we have assumed, then for that lambda, for a fixed lambda, because we have assumed the lambda is a fixed value here. If lambda is fixed, then if lambda is constant term. The V load we already know for each time. Lambda is also we have assumed constant. And in operation problem, if we have something constant, we can avoid. We can take it out because it will not affect the result optimize output of the optimization problem. Here you can easily see that term is constant, so this is dropped, and then we are left with this term. And this inner part, this one, this is only with respect, this is over time. And for each generator, we can do this. We can solve this separately for each unit, each generator. satisfying this constraint for each generator. Now it becomes a very simple problem. Two-state dynamic program. There are only two state, either 0 or 1 for each time block. Let's say there are 4 time blocks, 1, 2, 3, 4. And for each time block, we have only two states, 0, 1, 0, 1, 0, 1. Now we just want to find out what should be this path, optimal. Where it should be, what should be that path. We, in unit component which we saw using dynamic programming, there were so many states. If we take all the combinations, then 2 raised power n minus 1 combinations into number of hours 4. But here we have only two states. Only two states. 2 and 4 hours. So 8, total 8 combination. It's a very small problem, right? The problem size is a simple problem. And this two state we can easily solve. We'll see how by using this. So we can see here if ui is 0, then this total function becomes 0. If ui is 1, then it becomes fi pit minus lambda t pit. This minimum of this. And because we want to find minimum over these two, if this is 0 and we want to find out minimum, if u is equals to 1, this can be 0, positive or negative. If it is positive, then minimum of 0 and positive is 0. That means unit should be off. So what is the condition when the unit will be on? Can you tell? When will the unit be on? So what should be this value, 0, negative or positive, for the unit to be on? Because we want to find the minimum of these two combinations, these two states. Right? Here it is 0. And if we want this to happen, then its value should be less than this. Then only it will, because we have used a minimum here. And for it to be minimum, for it to be selected, it should be even less than 0. That means it should be negative. It should be negative. If it is negative, then minimum of 0 and a negative value is negative value. Then this will be selected. That means the unit will be on. That's why it is written for the unit to be on, this should be negative. So it's this two-state planning program. For each time we can check this value. We can calculate this value, and if it is negative, then we can say that the unit should be on. And if it is 0 or positive, then we can say should be off. And this is also clear from here. If we say that this is negative, that means lambda t is greater than this. That means the assumed this lambda which we have assumed, which we have fixed here, this lambda is greater than the incremental cost of the generator. And if the lambda is greater than the incremental cost of generator, that means the lambda should be reduced. This generator it's economical to turn on this generator, because turning on the generator will reduce the lambda. Correct? Is this clear, this point?
Yes, sir. Yes, sir.
So only when the cheaper generator is turned on, then the lambda will reduce. The same thing. This constant is saying the same thing, that the if it is less than zero, then the cheaper generator should. This will happen only when the cheaper generator is turned on. This is the same steps, all these steps. So I think you would have seen it, gone through it in the lecture. Did you find any difficulty in this?
No.
Easy to understand?
Yeah.
Okay. And same thing here. We start with, we are saying that it's a dual operation max over lambda and min over P and D. This is Lagrange. So step one, we are solving this problem. Considering, when we are solving this, we are considering that lambda is constant. And then once we get the lambda, sorry, lambda is constant, so we will get the P and U. Then for solving this step two, we consider that this P and U are constant. And we find out the new lambda.
Lambda.
Correct? Yes. So by using the gradient descent. So we are first solving this minimization step by assuming the lambda. We can set assume any lambda. If it is zero, then all these equations will be zero here, and we can easily find out p value. And then we have to check this constraint also. If p comes out to be negative, then it is not possible. We have to turn it off. And so we can find out this value then. Once we find out, so from here we are finding out p. And from here we are finding u. And then for this constant, for this p and u considering them constant, we are finding this lambda by using this. Where dq lambda by d lambda is this, the constraint, power balance constraint. Yeah, once this is done, we find out lambda, then we have to calculate this duality gap. So this one was our dual. This one is primal and this is our dual problem. We can see here we have relaxed that constraint, this power balance constraint, and we are considering it in this. For each sub problem, this is our sub problem, which is simpler without any, and this was our original problem. And as the iteration goes on, the gap between these two will reduce. And if it reduces below a certain tolerance, we can say that yes, we have achieved the minimum. We have reached the solution. The next one was this hydrothermal scheduling. This is also very, now we have been used to it. We have been operating our system for so many years. So it seems because a lot of experience, we are able to schedule these thermal plants with coal. But now also it happens sometimes that because it's uncertain, there are several things. We don't know how much rainfall will be there, what will be the weather. If it is, let's say this year is most of the states have received extreme rainfall, very heavy rainfall. Sometimes it's a drought year. and rainfall is very less. But we don't know that. And there are so many constraints in hydro. There is a water year, right? We have financial year from March to April. Sorry, April to March. Similarly, we have this water year also. For hydro scheduling, we have water year.
Okay.
Starts from June.
Okay.
June to May. Because June, July, August, September, these are monsoon season, right? Four.
Yes.
Because monsoon is there, the dam will be filled. So for filling the dam, we have to empty it, right? First. But that is not so easy. If we think, let's say if we made a wrong prediction, IMD made a wrong prediction that next year there will be very heavy rainfall. Okay, more than average, we can say. More than rainfall, expected rainfall would be more than the normal average rainfall. Then what the scheduler, one who is scheduling hydro will do, will try to empty the dam so that it can be filled again because rainfall will be more. We want to even avoid floods also. So it will try to use the entire water by the end of this water year. And then again, because he knows that in the monsoon, it's a prediction is good monsoon. So again, the dam will be filled. But if this prediction fails and the rainfall is below average, but the scheduling is done based upon above average prediction, then there will be problem. So all these problems are there. So this is one of the problem. And dam need to be they need to release the water before the monsoon season. That has to be done because otherwise, if dam is full and there is heavy rainfall, then the water has to be released. Gates of the dam needs to be opened, and that can lead to flooding of some villages. Many places it is happening this year. Even in Rajasthan, where this time rainfall is 50% above the average till now. So this is very uncertain. All these things we need to take care. So hydrothermal scheduling is of two different time scales. So one is long term and one is short term. In long term, we need to see the forecast of water resource and what will be the water release. We need to take multiple season, consider all the seasons based upon here the challenge is this meteorological cycle, hydro cycle, and then statistical analysis based upon the previous historical data of several years, 30, 40 years you have to consider. That's why it's very challenging. And then short term is for daily, hourly scheduling of generator. We want to minimize the cost. Here we know normal summertime, yeah, summertime, it depends on the location of the hydro plant also. Uh, in in summertime, you find water inflow is there because of the snow. Water inflow is quite high. Mm, this thing we, although it's uncertain, but next hour we know what.
Sir,
what
your voice is not clear.
sorry, is it clear? Wait, wait. Again, this is a network. Is it clear now?
Yeah, yeah.
Uh, Today, its network is creating a problem here. Internet is again, it is creating problem. Sorry for that. So it's also uncertain. It's not under our control. That thing which we are discussing. That's
Starting,
why
starting.
scheduling is a very difficult problem. And now operational. This is hydrothermal, but renewable is another. In this course, we are not dealing with that, but this is based upon what we have been doing. This course is based upon the book Wood and Willenberg, and its first edition came in 1990s. So at that time, this was it was a actual challenge, hydrothermal scheduling, because computers were the so good solvers were not available because of computational challenges. We had to resort to these different methods which we are discussing right now. But now these methods are not used. Now so many things, advances have been there, and another this uncertainty. It's a separate course for that, renewables. How to schedule these renewables? That is another challenge because they are even more uncertain. We don't know what will happen next hour. To certain extents, we can make some prediction based upon historical data, but still, it's always fraught with uncertainty. So here, in hourly scheduling of generator, we know these things. Water inflow, we know unit availability. Whether that in one hydro plant there are several units. Even similarly in this thermal plant also, in one thermal plant there can be a number of units, 5 units, 2 unit, depending upon the size of the thermal plant or hydro plant. In some hydro plants there can be even up to 12 units. Big hydro plants. They have 12 turbine generator sets. So sometimes some units are on maintenance, and depending upon the water release, how much water is to be released, if considering all the parameters, the unit availability is also known. And this can even be uncertain because certain times, even when a unit is being used, certainly there can be some fault. We don't know. We call them forced outages. There can be forced outage, and that is uncertain. But here we consider that yes, we are not considering that forced outage thing. We are considering the planned outages. We know the unit availability status, then we also know the load. All these things are known, and we want to find out what should be the release. How much water should be released from the hydro plant. So this I told that long term these are the challenges. In short term, this water inflow forecast, and it depends. In summer, if Himalayans we have dams in Himalayas, then how much snow is going to melt, that needs to be predicted. Based upon that, inflow will depend upon that. And even in monsoon season, the rainfall also is another problem. So weather forecast has to be uh, good enough to accurately predict all these things. And yes, these are some of the things that we need to consider. We don't want the hydro plant to be overutilized. If we overutilize, that means we are uh, releasing all the water, most of the water. Then there is no water for the dry season, dry spell, where there is no inflow. Then it will create problem. Then underutilization, if we do not release water, then the river may not even complete its course. The river has to reach. And the river navigation also. In India, we don't have that much navigation. River navigation is less right now, although now government is doing these national waterways they are creating in river Ganges. But in most of the rivers, we don't have navigation river navigation that much. But in European countries, they have several, some of the European countries, they heavily depend upon these waterways. They have a good connectivity of water, road, and this, you can see, uh, is metro, underground or maybe overhead. These are very good. They have good connectivity. Anywhere you can go by waterways and just deboard, and the place where you deboard, you will get another metro or some bus or something. Waterways is good because cost, there is no fuel cost. Okay, yeah, so these are the several constraints which we can. So many things need to be satisfied, and apart from these, sometimes there are these disputes interstate. One river which is shared by two different states, there are disputes between them. That further complicates the problem. So many things are there. Okay. So in this we first, this was the hydropower plant model. Here, this is called penstock, where the water goes into the turbine. Using this channel, it's a channel which carries the water. And difference between this forebay and afterbay is the gross head. And after this, we use the net head for calculating the power output of the power plant, hydro plant. And in this gross head, there are losses because of friction in this penstock, this inlet, and this draft tube. All these things will reduce this net head. And also, if there is flooding, then this level increases. So this reduces. The output also reduces. Further, the output is also governed by this. Then next thing is efficiency of generator. That is quite high. But the loading, unit loading also affects the output, the efficiency. If the unit is the loaded, the inlet, the inflow of water is less in the penstock, then the efficiency of turbine is also less. That also need to be taken into account. So many things are there. Yeah, and this losses are more when the head is low and penstock are very long. The next thing was this turbine. Different types of turbines are there. I mean, there are two types. One is this impulse type. Impulse type because it the nozzle through which the water is coming, because nozzle creates high pressure water stream, and that drives the turbine. That's why it is called impulse turbine. But in reaction, the mechanism is little different. So these are of two types, and these propeller or its and its advanced version is Kaplan. It is it has more higher efficiency than propeller. So these are used for low head, and this Francis is used for medium, and Pelton is used for high head. But, so, today there is so much uncertainty. It's happening on its own. There is some problem with my touchpad. Yes, touchpad of the laptop. Sorry. Let me just share Sorry, we were here. And this we will discuss. And then in hydrothermal scheduling, there can be different cases. It one this first one which we discussed, this assumes that there are two generators. One is hydro and one is thermal. And the hydro generator is a very large generator. And the coal is only there to support the hydro for few hours. And although this example is considering only this two two unit problem, one is thermal and one is hydro. But actually it can be extended to more number of thermal and hydro. And there are few countries which have very huge amount of hydro resources and they are mostly run by hydropower. And this type of example, this example or this case first, which we discussed, is more relevant for those countries where hydropower is the major source for supplying the demand. Can you do you know any such country where hydropower is quite large and it's very significant amount of demand is met by hydropower? First question is, does India has does
No,
India
we,
falls in this
no,
category?
obviously not.
Oh yes, India falls in
Only
second category.
the 25%, I think. We are generating only 25% of the total power through hydel.
Yeah, so can you do you know any such country where the hydropower is very dominant? It's very from significant amount of energy is met by hydro generation.
No idea, but heard that the France is using almost 90% of their generation through nuclear.
Okay. Yes, yeah, France has a, uh, very high nuclear penetration, but now I think that has changed. I don't know exactly, but now the dominance and reliance on nuclear is reducing everywhere because of several reasons. That one is risk is a very important factor, but other thing are the dealing with the nuclear waste. That is a very big problem. It is still a problem because the waste it takes years to several years, more than 100 years to decay completely. That's its disposal is a very big problem. Still, that's why in most of the countries, new nuclear plants are not being considered.
Which is the country where it depends on hydel? Hydro?
There are several countries. One such example is Canada, because Canada is called the land of country of thousand lakes, something like that.
Okay, okay. Now you're
Even
talking one of the.
Finland is one of them.
Okay,
Then Bhutan is there, our
okay,
neighbor.
okay. Okay.
Bhutan and is mainly Bhutan. It's most of its generation comes from hydro, and it exports to India also. And even India exports to Bhutan. Now India, Nepal, Bhutan, and Bangladesh. We have interconnections, transmission line interconnections with these countries. So when there is a Two in both ways. Wherever it demand is there, demand is more. When hydro generation is more in Bhutan and the demand is less there, they export to India and vice versa. Similarly, Brazil is also another country because of Amazon River. Its Amazon basin spans in Brazil. A lot of so a significant portion of Brazil is covered by Amazon River. So they have a lot of hydropower. Around 60 to 70% of their generation comes from hydro. And all these are some countries. There is a list of such countries. There is one professor, Mark Jacobson, from I think Oxford, no, Stanford. He is working on this. He has written book also on 100% clean renewable energy, so wind, water, solar. He is tracking it for so many years. So it is. He says since even America is doing it. Okay, this in America there are several independent system operator. One is CAISO, it is California Independent System Operator. It is operating in California region area. So around for continuously for not continuously, but in past few months for 100 around 100 days. It is now more than 104 or something. For 100 days, the entire demand for 5 to 6 hours
Okay.
was met only by renewables. So water, wind, and solar.
But country like us, maybe it is not possible because we need a lot of inertia, something like because the load is continuously going to change, the demand is high. Maybe is it going to work in our case?
Actually, this 100% generation from wind, water, and solar, this is not happening for 24 hours. First of all, only for 5 to 6 hours this was happening, and this will happen only when there is excess renewable generation.
Yeah.
When temperature is what happens with solar and both wind also, but mostly solar, what happens when temperature is high or even low, very low temperature and very high temperature. When temperature is very high, then also efficiency of solar is less. And when temperature is low, irradiance itself is low, so output is low. Wait, you will find the generation of solar is maximum during springtime. That time there is excess solar generation. And during winters, you'll find generation is very low. That's why capacity factor of solar is not good. And what happens when there is high temperature and if wind blows because of pressure difference. If there is high temperature throughout the country, pressure difference is not much, then wind speed also reduces. So output of wind is also affected in that case. So that's why this solar and wind, when their output is less, then and hydropower is also limited. Whatever generation is there, installed capacity is there, we cannot increase it. It requires so many years, 10, 12 years, 6, 7 years it takes to build one hydropower plant. So when the output of solar and wind is less, then other generators are used. They use gas. Gas generation is quite high in US.
Costly.
Gas based, they have gas based, oil based, and then now batteries are also helping to meet the load, especially when the ramp up and ramp during the ramp up and ramp down requirements in the morning peak. when the solar is going down and the demand is increasing, at that time battery is discharged. And they charge when there excess during daytime when there is excess solar. The batteries are also now helping. India entire, there is one state where this wind, water, solar is working for one state.
Tamil Nadu.
You're close. It's neighbor of Tamil Nadu.
Okay, okay.
It's Karnataka.
Karnataka. Okay, okay.
Yeah, Karnataka there is hydro, quite a good source of. They have hydro plant and they have means new. They have built new pumped hydro storage also very big. I think around 1.6 gigawatt something capacity. So
There is
few.
wind is more in Tamil Nadu. Most of
Yes,
the
Tamil Nadu is leading India in India. Tamil Nadu is having that. Sorry, what again? What is happening? Tamil Nadu is leading in wind energy.
yeah.
There's very highest installed capacity in India. Wind is in Tamil Nadu. Uh, Karnataka in few months of a year, Karnataka experiences excess generation. So they are managing the variability of renewable using hydro. When the renewable generation is, let's say, for next hour reduces suddenly, they are using hydro. So with hydro, renewable, this solar and wind, they are able to manage for few hours. It happens for few hours that their generation is even more than demand. They are exporting power to the neighboring states.
But
They're
that is
not even.
intermittent in nature, particularly wind. It's highly intermittent. So control will be, I think, a difficult task for
Yeah,
them.
that is why hydro is important in that case because hydro, the ramping requirement as which is there for thermal is not there for hydro. Hydro can ramp very quickly.
Yeah.
It's happening today and much. So hydro can ramp very quickly. So that is not a problem for hydro. Let me change the. There is some problem with the touchpad of the laptop. Let me share again.
Okay. So in the last assignment number 4,
Okay.
there is a
Is
question
the
given.
is the presentation visible right now?
No, no, no.
No. Okay. Now?
Now okay.
Okay.
Yeah.
Yes. You were saying about assignment 4.
Yeah, assignment number 4.
Okay.
Question number 7.
Let me just open that assignment. Can you read that question or let me just see what
Yeah,
is
yeah.
that?
For economic dispatch that neglects both the line losses
Okay.
and
Yes, yes. You had posted it in the discussion forum also, right?
yes, sir.
Yes. Yes. Yeah. So actually, in that question, there are multiple answers. The two
Yeah,
answers,
yeah. Yes, two
only one
answers are
answer is
there.
given. But
Uh,
two options are correct in that.
Two options are correct.
Yes,
In
both
fact,
of them are correct.
yeah, when you neglect losses, obviously generation should be equal to demand. It
Yes,
need not
yes.
be an economic dispatch problem. It can be, same in the case of power flow, whatever you consider. But specifically, it is mentioned economic dispatch. So that is why I selected the other option.
Yeah, so it has actually multiple. It has it's a multiple choice question.
Yeah, yeah, yeah. But
Yes,
answer is given
they missed out one option.
yeah,
That's the problem. Otherwise, that concern is correct. Both the options are correct in that. It's a
options are
multiple
correct.
choice. Yes,
Yeah,
that is correct. Yeah, so I was saying about Karnataka, right?
yeah, yeah.
Yeah, in Karnataka, they are actually exporting the power only by using renewables, wind, water, and solar. During few hours for few certain month of the year, they are able to do that. And this wind has inertia, and hydro also has inertia. Solar doesn't have, but
Yeah.
by using these in inverter control, we can use that virtual inertia also. Now new inverters, PV inverters, they are also having that virtual inertia also.
Can they
But
manage that much huge load?
sorry,
Can these inverters, whatever, can they manage that much huge load variation?
oh, for that even the install capacity of solar also has to be high. So it depends upon the rating of that PV plant.
Okay.
Certainly, it will not
Okay.
be 100%. It is not
Yeah, yeah.
possible. So there
And
is
one
limit
side they are
to
facing
that.
water crisis in Bangalore.
The water crisis, sorry.
In Bangalore, there is a water crisis right now.
Okay. Means water availability.
Availability, drinking water availability.
Okay,
So
okay. So they are, what are they doing then for water? They're getting water from outside,
no, 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 no. We have some reservoirs like Kaveri Reservoir.
but reservoirs are the amount of water in that reservoir is reduced
Yeah,
because of less rainfall this year.
yeah.
Yeah, it's a problem in Mumbai also. Mumbai is also fully dependent upon these lakes nearby because Mumbai is near to coast. It's a coastal city. Coastal, we cannot use the groundwater.
Yeah.
So entire water is the water which is filled in these lakes during the monsoon season. Fortunately, this year uh,
There's a lot of
around
rainfall.
yeah heavy rainfall. So 97% of these reservoirs are filled. So for next 1 year, sufficient water is there for Mumbai. But Mumbai is heavily dependent upon these rainfall. If rainfall is not enough, then water crisis is will certainly be there in Mumbai. So yeah, it's a problem now. Climate change is a very big problem.
Yeah.
So yeah, I was saying this one. First case was this, where the hydro is very large and thermal is there only to support the hydro for few hours. So here assumption is that the hydro has enough power capacity.
Okay.
Suppose we have 24 hours load profile, right? And this, let's say the peak demand is 300 megawatts. Then this hydro capacity is greater than equals to 300 megawatts. It can generate anytime this much amount. But The constraint with the hydro here is this is the total energy requirement by the load for 24 hours. This area under the curve. Okay, 24. But hydro for 24 hours, hydro cannot provide this entire area. Maybe it can provide only this much. So this area needs to be supplied by thermal. This area. All the power capacity is there, but enough storage is not there. The enough water is not there in the hydro plant. So part of the demand needs to be satisfied by the thermal generator. So that is the problem here. In this case, we want to minimize the cost of running the thermal generator. And we also don't know here for how much duration that thermal generator should be on. And if it is on, how much should it generate? That is the problem here. We need to find out these two things. One is this duration for which the thermal generator should be on. And when it is on, what should be its output? So these, it's a simple problem here. Again, this is our, we want to minimize the cost of total thermal, total cost of generation from thermal.
Thermal
So
generation.
this is power into time energy, the total energy cost. And subject to constraint that this difference of energy, the energy of load minus energy which hydro can supply, which is equals to some E, this difference. And this difference should be supplied by the thermal generators. Yes. For this time, T thermal. And we don't know this. We want to calculate this. So this is the that duration ns, number of such interval. Each interval is of delta t time, and what should be this tt? The
In
ns
our
will
case,
be,
is completely different.
yes, in
Generally,
our
what
case
we
will
do
be,
is we run the hydel generators, something like a support to thermal generators.
yes, correct. It's opposite.
Yeah.
Yes, that is correct, because we generally, hydros are generally used when lot of ramping is required.
Yeah.
When this evening load we want to cater, as solar is reducing and thermal is increasing. Sorry, load is increasing.
Load is
At
increasing.
that time, thermal cannot increase because of ramping constraint. It cannot increase suddenly.
Yeah.
Then the hydro comes up because we don't have storage right now in India.
Yeah.
It's very less. But now so many new tenders, SECI, the Solar Energy Corporation of India, has come up with several tenders for energy storage. Gujarat, GUVNL has also come up. So now within next 2 years, the install capacity for battery energy storage in India is going to increase. Further, that pumped hydro storage also, CE has approved 2.6 gigawatt of pumped hydro now. That has started construction.
Okay.
So within next 5 years, the storage will install capacity of storage will increase, sir, and that will help during to reduce this ramping problem. Because to avoid that ramping problem, that as the because renewable penetration is also increasing. Our goal is very high. It's very ambitious. 500 gigawatt of
What
renewable
by
twenty
non-conventional?
by 2030.
2030. 2030.
So
Yeah, it's
if we
so good.
add that much renewable,
Yeah,
then ramping requirement will be very huge
very huge. Yes.
because load is also increasing.
Amazing. Yes.
By
The
2030,
same.
load will also increase. Data centers are coming up, new manufacturing. centers. So data requirement is sorry that
Load requirement.
load requirement is demand is quite high. It is going to increase exponentially by 2030. So
Yeah, yeah.
load is increasing, renewable is increasing. So net load is also going to increase,
Great. Yeah.
and with it will increase the tramping requirements. For that we need storage. That's why the CEA has planned this. If we have
Yeah.
storage and adequate pump storage and this we as per CEA, India has a potential of around 176 gigawatt of pumped hydro storage.
Yeah.
And that is not exploited yet. We have only less than 10 gigawatt of I think not even 10 gigawatt. We have only less than 5 gigawatts of pumped hydro storage right now operational. So that will certainly help. So here we are just this is objective function. We are subjecting it to this constant. We can write the Lagrangian function and differentiate. Then we will find that for optimal, what should happen? The generator, thermal generator should run at its constant, should run at constant incremental cost. If incremental cost is constant, that means the output is constant for thermal generator. It should generate same, it should be generating, let's say PS star, optimal PS for NS duration. So if it has to generate PS, then we can easily find out NS. Because energy produced by thermal will be equal to PS into NS, number of hours, NS. Once PS is known, we can easily find out NS also. We will do one numerical on this. It is an example from the same book, Wood and Muhlenberg. And if we optimize this, if we maximize, if we minimize this cost function with respect to PS, we can find out PS will be this. AP square plus BP plus C. So this C and A root under root C by A. So this will be PS. It's a very it's a simple alone hydro. If we have only hydro, then also it's difficult to meet the demand. So if we have some other generator, we can hydro can provide the demand. So that is this case when hydro is quite large and thermal is there to support. Now the opposite case is when hydro is less, means hydro it's opposite almost. It, it's relevant to what most of the countries have. Most of the power grid, if not now, at least, especially at that time, yes. And to still now also 60-70% grid, they have this same situation, similar situation. Thermal generator or conventional generation is still a significant portion of the generation, and then hydro is less. So here it's opposite. Thermal units are large and operated for the entire duration, and hydro is there to support.
Support.
So thermal generator in this case, what you are doing, this composite cost function which we have studied. So all the thermal generator they are represented by one single unit, and then it becomes a two-unit problem, one thermal and one hydro. But only thing is hydro is here small. The cost function is same here, but now the constraints are different because here we have limit on what total discharge from hydro we can have on a daily basis. This is a total Q discharge, Q total which is possible over 24 hours. That is for one day. What is it's a hydrothermal scheduling with limited storage. Limited, not limited. Limited was there, but it is in terms of total discharge. It is very less here. Mm, So we have only this much Q total. And another is the power balance equation. Power should be balanced. So whatever load is there plus losses should be met by thermal plus that steam or hydro plus thermal generator. This steam or thermal generator. Then water discharge limit. This is the power rating, and this we can say energy
Q total,
rating. Sorry?
power balance equation.
No,
Power
no,
balance
sorry.
equation, the
It
total.
should be, what should be here? What should be this?
Uh, so balance equation means zero.
Yeah, it should be zero. Sorry. Actually, I would, what I think I had copied this equation.
Ah, yeah, yeah.
And yeah, so I forgot to remove this. It should be zero.
Zero, zero.
Yeah, sorry. I will change this and upload while uploading. And this Q has to be within this minimum and maximum value.
Yeah.
For large hydro, generally there is a minimum generation also. There is, let's say, in this Maharashtra, we have this Koina Dam, Koina power plant. It's a 1.9 gigawatt hydro plant.
Okay.
Its minimum generation is 20 megawatt. It is always there, almost throughout the year. Because
But the thermal power, there is a limit, there is a constraint for minimum.
uh,
Because
there is no such constraint for hydro, but it is because of the other this constraint which we had seen. These where is that? Yeah, this because of this we need to satisfy not power generation. This we want to satisfy this, right? Because of this, there is some minimum generation
okay, okay. So you need to
for
release the minimum amount of water.
yes, yes.
With that,
So
you are
that
getting
is
20 megawatt.
yes, yes.
Okay, okay.
This is required. Also,
There
that
is
because
no
it Koina Dam is
technical,
on. No, no, there is no such technical. It can work on zero
technically.
also. No, no,
Yes,
no.
yes.
It's not a technical constraint.
Okay,
It's a policy constraint.
okay.
Other constraints also there are other. It's because of that. It's on Krishna River. Right? So there is a tributary of Krishna, and
Yeah,
in that Maharashtra, Karnataka are sharing this river, right? So they have Krishna Water Treaty.
yeah.
They need to because of that also they need to satisfy something. They need to release certain amount of water to for Karnataka. So some things are there.
So on a continuous basis.
That I don't know exactly. On a continuous basis, might be it should might be continuous only. I don't know exactly, but yes, these it is apart from technical constraint. This is not because of technical constraint. This minimum. It can be zero. So this was water discharge limit, and so for these are the two equality constraint. For these equality constraint, we have two multiplier, Lagrange multiplier. One is lambda and one is gamma. Gamma for this, gamma for power balance. Oh, sorry, lambda for power balance. Generally, we use lambda for power balance. Gamma for this total discharge constant water. This is related to this satisfaction of this equality constant, and lambda t that is for each time power balance. It is concerned with the power balance. So if we differentiate again, same we can write the Lagrangian function. We will move these two equality constant here. So plus lambda into this plus lambda t summation also, and gamma into this constraint. Then if we differentiate it with respect to thermal and hydro, we will get these two equations. Now these two are interdependent because of this loss. And also in this equation we have lambda also, gamma also. And this loss, this lambda is unknown, and this loss is also function of this P hydro and P thermal. So it's a non-linear lambda into two variable product of two variables. That is, whenever there is product of two variables, then we use this iterative methods. Right? That's why we are using this lambda gamma iteration. Once we fix lambda and then solve the equation, and lambda will tell us about this, right? Then we, for a particular lambda, we solve the coordination equation, then we try to see this and again project the lambda, increase the lambda as we have seen in lambda iteration. Then try to minimize this gap, make it zero. Try to bring it to zero. Once it is zero, then we move on to Q. Check this for that particular lambda. And then it will keep on, these two iteration will go on like this till this constraints are satisfied. All the nonlinear problems, their solution methodology is based upon these iterative methods. Power flow is iterative method. Solution for power flow is also Gauss Seidel, Newton Rapshon. All these are non-linear because we have. Can you tell what are the non-linearities in power flow equations? What are the sources of non-linearity?
Partial equation means the cosine and sine terms.
Only is that the only source? Yes, cosine and sine they are non-linear function, so that is correct. These two are source of. Let's say these two will come up only in the polar coordinate. Let's say if I use the rectangular coordinate, then I don't have these cos theta and sine theta. Then still the power flow is non-linear. What is that source of other non-linearity?
Because the values are complex values. So
No, not complex. We have P and Q equation, right?
yeah,
In the form, we will write them in the form
these
of
are
here
expressed in
also.
terms of voltage and voltage in terms of voltage.
But in polar coordinate, we are writing this voltage as like this, right?
Yeah.
In rectangular coordinate, we will write it as like this.
So A plus JB. Yeah.
Yes. So it will be in the form of real and imaginary part,
Yeah.
these equations. But the source of the non-linearity is apart from cos and sine, there is one more source of non-linearity, and which is this product of voltages, Vi into Vj. This is also non-linear because Vi is not known, Vj is also not known.
Not known. Yeah.
This product is and it's a major source of. This is the main source of non-linearity. We can use polar, this rectangular coordinate, but this is non-linear. Even after using that, we are still we still have this problem.
Yeah. But once you select, say, some uh, slack bus,
Hmm.
you can fix one of these voltages.
No, but that will happen only for one voltage, right? One bus.
One bus, one bus.
But that is already known. For that bus, we are not even calculating the voltage.
Yeah, that is already
Let's
known.
yes. So we have how that is one question also. How many unknowns do we have?
Hmm.
Let me just finish this. We will come to that. That's one question is also there.
Okay, okay.
Okay, so this is clear, right? You would have understood this.
Yeah,
And
yeah.
it is easy. Then this limited generation energy supply one this ED. All these problems are a similar structure. You will find objective function.
Yeah.
Only this is changing little bit than constraints.
Yeah.
Solution method is same. You write the Lagrange function, move these constraint into Lagrange function by using dual variables, and then use iterative methods. Only the nature of constraint is changing, but solution methodology is similar. So here we are using gamma search. Yeah, so let's now discuss the same thing. It should discuss AC power. We were saying these methods. Right? Non-linearity was because of this voltage product. So we have what are the unknowns and knowns?
Voltage magnitude, load angle,
So we have these
and
three buses, right?
yeah,
On
slack
slack
PV amplitude.
bus, let's say first let us write what are the known parameters for slack bus. What is known?
Slack bus voltage magnitude and then load angle.
Yes, so voltage magnitude and angle,
Load angle.
both are known. So we generally take it as 1 angle 0.
Yeah.
So why do we need a slack bus?
Slack bus
There are,
because we need a reference to calculate the other remaining angles.
yes, correct. So one is for reference. It's a reference bus. So
With
slack bus
respect to
and
this, we will
reference
calculate the
bus.
other.
Yes, slack bus and reference bus can be different also, but here we are generally consider slack bus as the reference bus.
Yeah.
Reference one is for reference, angle reference. What is the other role of slack bus?
Otherwise, slack bus has to supply the losses.
Yes, correct.
But it should be a generator bus, obviously,
Yes,
and should have sufficient generating capacity to supply losses because we don't know the losses.
correct. That is correct. So that is these are the two main reason why we go for why we need a slack bus. So here we know voltage, magnitude, and angle. What are the unknowns here?
Power injections, real power and reactor power injection.
P and Q. And what about PV bus? What are
PV
known?
bus P and V are knowns.
Yeah, P is known, V is known, and unknown.
Q and delta. Q
Yeah,
and
so Q and delta. Yes. PQ, P is known, Q is known,
Q known, V and
delta.
delta.
Yeah. So now, how many unknowns are here total? So no, what was the input for power flow? What are the inputs and what are the output? What are the inputs for power flow and what are the outputs? What do we calculate?
Output is obviously voltage magnitude and load angle. Voltage and angle,
Yes, voltage magnitude and its angle.
load
And
angle.
input is
Input is um, the power
yes. So injections, P and Q
or
injections are the input.
injector.
Yeah. So how many knowns are there? What are the if let's say there is N bus system and we have M generators,
Yeah.
then how many knowns are there? How many P and Q are known? What are
Say
the
N bus
knowns?
system, M number of generators. Out
Yes,
of this M
M.
number of generator, one generator should be slack bus.
Yes, so let us so remove
So
one. Here left with M minus one.
M minus one number of generators. M minus
Yes.
one generators, we require that angle.
No,
So
first let us uh, for M minus one. What are the knowns? First, we are uh,
it's a
calculating the
generator
number
bus.
of knowns.
Generator bus knowns are P and voltage.
Yeah, so M minus
Unknown
one P and M minus one V
V
values we know.
known.
Yeah, so whatever. Then we have
Right.
this is for PV bus.
PV bus. Remaining PQ buses are N minus M.
Yes, n minus m are PQ buses.
PQ buses.
Here, what are the known?
Knowns are
P
P
and
and
Q.
Q. Voltage, magnitude, load angles have to be calculated.
Yeah, so this is n minus m, n minus m.
N minus
So
M.
how many knowns are there? Input for our power flow is P and Q. So how much P plus Q we need?
This
So how
is
many
N
P
minus
is
1.
n
P is
minus
N
1,
minus
yes.
1.
P is n minus 1 by removing one slack bus. So
Q is N minus
n,
M.
n minus 1 P and Q is n minus m.
M.
So total we have 2n minus m minus 1. Correct. And similarly, what are the unknowns here? For PV bus, what is unknown?
PV bus unknowns are angle, mainly angle and reactive power.
Yes,
The
angle,
output is
angle and
angle, so
voltage.
M minus 1 number of angles are to be calculated.
M minus Q. Oh, so okay, we are only looking for delta and
Voltage
V.
and angle. Yeah, yeah.
Yes, so this is
So angles again, N minus M here.
n minus m. Yes, n minus m
And
angle.
voltage is N minus M.
Voltage is also n minus. Yeah. So
So
total
total
again
N
delta
minus
is
1 deltas.
yes, and what is this voltage?
N minus M.
Is n minus m. So this is also 2n minus m minus 1. So what will be the size of Jacobian matrix?
Size of the Jacobian matrix, yeah, this one only, because PQ angle delta, so 2n minus m minus 1 by 2n minus m minus 1.
Yes, so Jacobian matrix is a square matrix. So it is
Yeah.
2n minus m minus m. So we already discussed as this Gauss Seidel has a linear convergence, right?
Yeah.
What about Newton-Raphson?
That means quadratic.
Yes, Newton has a quadratic convergence. That's why it converges fast. It has a quadratic. In Newton's, we are updating the Jacobian matrix every iteration.
Yeah.
But in fast decoupled,
That is constant, made constant.
yes, we are only calculating that B dash and B double dash matrices only once.
Yeah.
Only one. After that, it remains constant. And we can find out their inverse using Gauss elimination.
Triangular factorization and Gauss elimination methods.
Yes. Gauss elimination, LU decomposition.
Yeah.
Generally, we don't use Gauss elimination. We use this LU.
Only factorization.
But LU actually is it's an output of Gauss elimination.
Yeah.
So while doing LU, we are doing Gauss.
Yeah.
Once we calculate their LU, we can easily calculate the inverse without explicitly calculating the inverse. We don't want to do inverse. Inverse is it's a computationally intensive operation. And for a large network, power system network is a very large network. Jacobian size of Jacobian matrix is
Very, very high.
10,000 cost. It can be 10,000 cross 10,000, 20,000 cross 20,000. Then taking inverse is not a good it's not a good choice. It will take a lot of time. And so if one inverse is taking so much time, you can imagine one iteration, how much time that single iteration will take.
Yeah.
Right? So it's not a good option. Okay, now let us move to question. And last question is that numerical also on hydro. This is a simple question. Most of the things we already discussed.
Yeah. There's no sense in more than 1,000.
Yeah, more than 1000 because this one, which one is this?
I had plans.
Which type of turbine? I had we use this impulse type.
Impulse. Yeah.
Impulse type and Pelton is the impulse type. Impulse time they have an impulsive force on. Because of that force, they are able to move. Because when a head is very high, the kinetic energy is very high.
Yeah.
mgh it increases, and that kinetic energy is sufficient to drive the turbine.
Okay.
But when head is low, that kinetic energy is not sufficient to produce an impulsive force. So that's why another mechanism is the reaction turbine are different. Their principal operation is different. They don't use any this impulsive force. They use another concept. It is similar to. And sometime you would have seen when you in a sink uh, where we washed utensils. Sometimes you see water, it goes like a whirlpool.
Yeah.
Like when there is it's a vacuum kind of thing. When there is a pressure difference,
Yeah.
then water forms a whirlpool. It rotates. In reaction turbines, that pressure difference is created. And because of that pressure difference, it rotates. So their design is such that uh, there is a pressure difference below and above, and that's why they are able to that the turbine is able to move. Okay. Next one is in long-term forecasting of water resources, minimum duration of typical scheduling ranges. This is also very easy. It was written, but I didn't mention this. And so how much
Long-term forecast.
short term it is hourly
Hourly
scheduling.
basis. Yeah.
Long term
Long
is
term it's 1 year more.
yes, more than 1 year because we
More
need
than
to
1 year.
consider multiple seasons.
Yeah.
All the seasons we need to take into account. So minimum it is 1 year,
1 year.
1 year, 12 months. Yeah, this also we have discussed. In short term, hydro scheduling problem is solved by
And from
yeah, lambda gamma. Because of those, there are two equality constraints.
yeah.
One is that power balance
So
for each time block. That's why we have lambda for each time block. And then we have that total
water,
water constraint,
water consumption.
daily total water constraint, availability of water. That is only one constraint. We have gamma for that.
Yeah.
This also we have discussed. Newton's method as linear
Not
convergence.
linear, it's quadratic.
It is quadratic, so this is false. Then next is unit commitment using Lagrange relaxation is based on dual primal dual. Yeah, it is based upon dual optimization.
From development.
Fuel scheduling is linear, mixed integer, linear, quadratic, or none.
Scheduling.
Fuel scheduling problem.
Mm. Scheduling is different.
Fuel scheduling. How much fuel should be used? because that contract is there, right? That pay and what I forgot the name. Track and pay, something like that. Because the supplier will do a contract with the generator that I will provide you the fuel at this cost, and you need to use it.
Okay.
So the generator will have some inventory, and when it is using, then it has to keep a stock. So
Okay.
for that, how much fuel should be used so that the cost of fuel is minimized? That is a problem, scheduling problem. So let's say for a 3 week duration, each week how much fuel should be used and how much should be procured so that overall cost of fuel is minimized. So it's a linear program. You can solve it using LP. Objective function is linear. It is minimization of fuel cost. And constraints are also linear. The constraints are something like that. We have existing plus uh, purchase and minus usage. This is equals to existing. This is the actual fuel which is there. And we want to minimize the cost of this fuel. Okay. So how much should be purchased and when? And when to utilize it? That is a problem. So all these, that's a linear equation, right? It's a linear equation.
Yeah.
Similarly, the even the scheduling, the objective function is also linear. The map into price only. So that is also linear.
Linear program.
So it's a linear problem. Then next one is this we have already discussed, right? Size of Jacobian for n buses m generator system is
Qn minus minus
2n minus 1.
minus 1.
Yes, correct. Now we will discuss this last question. This is a numerical on that hydrothermal scheduling. It's a it's example 5 from chapter 5
Okay.
of the book. Do you have that book?
Yes, sir. Yes, sir.
You have hard copy.
Yeah, yes, sir. Yes, sir.
Which edition?
It is actually it is in the college. I have not verified it. So it's a old edition.
Okay, I think it would be, I think second, most probably second edition. Third edition came many years after the second edition. The
He is having
latest,
some online lectures also by Willenberg.
yes, he even based upon that book, he has provided the presentations also.
Yeah, yeah.
He has, yeah, recently those series of lecture based upon his third edition.
Okay,
That's
okay.
which is the latest edition. Yeah, those lectures are good.
Sir, can you open this lecture number 11?
Lecture number 11. Okay. Should I share that?
Yeah, yeah. I just
Just,
have some doubt on
just a minute.
that is regarding DC power flow.
Lecture number 11.
Lecture number 11.
Which do you remember timestamp?
Lecture number 11, power flow problem on DC network. Week 3.
Yeah. Yes, week 3, but at what time, around which time?
Okay. The, there,
So what is the doubt?
regarding the numerical problem that is solved for DC power flow.
Okay. Yeah, so in that, what is the doubt?
Almost at the end of that lecture.
Okay. And okay. Let me see that notes. It's better to open the notes. Because same thing is there in the notes also.
Yes. Lecture notes.
Lecture notes, week 3. Let me share that notes. Lamps. Sharing again. I hope you can see the notes. Visible?
Yeah. Visible.
So
I'll tell you the.
we'll go to the end first. Yeah, I've reached the end.
There is one problem solved.
Sorry, it's lecture 11. Yes, this one.
DC power flow. There is one problem solved. I'll tell you. Slide number 20. 16. I think it's the beginning. It's the beginning.
16. Yes. Okay.
Can you go to the next slide?
17.
Yeah, this is the Vibus matrix for the
Yes.
given system, right?
Yes.
So can you go to? Can you please go to the next slide?
Yes.
Yeah, you see that the equation.
Yes.
Is,
correct. You are right. I got you. When I was seeing this slide, even I was. You're saying that this matrix, how these are different.
when it comes to inverse, all the
Yes.
polarities have been changed.
Yeah. Correct. Same. Your doubt is correct. There is a mistake here. This matrix should not means this right side matrix is correct. Left side is not correct. Actually, the problem is we cannot directly use this y bus here. It is negative of that.
Yeah.
It B matrix which we use, which we get from y bus, and the one which we use in DC OPF, DC power flow, that B dash in DC power flow is negative of the y bus, the B matrix from y bus.
But when you solve from say something like the equations,
Yeah, then you will directly get this. You will directly get this in this form. You can see when you write this, right? You are getting this positive. All the diagonals are positive. If you write the equation and you form the matrix, you will directly end up here.
So do you mean B12 means the
Either remove J, only magnitude, consider only magnitude.
yeah, then only it will be possible. Otherwise, you take the
No,
negative sign there.
no, don't consider J, only B. Only magnitude you consider.
But see, for a line having some reactance,
Yes.
when you take the inverse of it,
Hmm.
you will get some minus J's into something.
Yeah, the problem here is we are not dealing here with reactive power. We only want P, so everything is real here. That's why we are not bothered about imaginary part. We only want the magnitude part. And that inverse is, that negative is coming because of J.
Of course.
Only because of J. Because we are inversing 1 by J is minus J. But we are not even considering J. We are only directly taking the magnitude of X. Don't
Okay, okay.
take imaginary part. Only take the absolute value.
So then this Y will be obviously susceptance, no
Yes.
conductance.
When you use Y bus, then this J term is there.
Now,
That's
why
why
I got the doubt is you see that Y is equal to some J into something.
yes.
Y
Yeah,
is
that's why
equal
it's
to
confused. It's little bit confusing here. Generally, students make mistake because
yeah.
when we calculate Y bus, then we consider imaginary part. We consider Jx and then take inverse.
But of course, if the say resistance is also given,
Yes.
you
So
will
I
get
yes, it is
both the
R
things.
plus Jx. We are only
R plus
considering
J.
the G plus JB
So,
part.
yeah, you will get conductance and susceptance as well. So
Yes,
when you
yes,
write Y bus like this, say minus 30J,
yes,
so the B value will be minus 30.
yes.
And say B11, B22 will be minus 20. But when you write that equation there for
Hmm.
this DC power flow, the
Yes,
B22 that should be positive.
yes, correct. You can
So
see here.
yeah, yeah, yeah,
That is why one method is which I told in when we were discussing this, week 3.
yeah.
I
Last week I
had
was absent. I
okay,
heard
okay,
that.
no problem. It's mentioned here also in this in this maybe somewhere it was mentioned that method.
The diagonal should be always positive.
Actually, there was one easy method. Directly you can. I don't remember that slide, but it was mentioned in lecture also.
Okay.
Maybe compare. I have. You can refer the presentation which I have used.
Okay.
It's mentioned. It's there. Maybe it's in week 2. Week 2 lecture.
Okay.
Let me check once. So directly, if you do matrices, you take incidence matrices A.
Okay.
You take diagonal matrix BD. Only take the magnitude, not imaginary part.
Okay.
Diagonal values. That is BD is 1 by X. It's a diagonal matrix.
Okay. So
Then
when you
you do.
neglect X, when you neglect that imaginary part, then there is no problem.
Yeah, so better to take directly do that.
Okay.
It's very confusing
Yeah, yeah.
because it's really very confusing. So we should know that it is not Y bus there.
So
It's
simply take
not
the
the
values
B.
and simply multiply the octagonal elements with minus
Yes,
1, you will get the
yes.
answer.
Either you remember that you have to take a minus, otherwise you
Yeah.
use that another method which does not, which don't, you don't need to remember these things. Directly it
Yeah.
will give you the matrix.
Okay. Okay.
Okay,
Then
shall we? Yes.
last time we are discussing about the reactive power.
Yes, yes. I remember your question.
Yeah, yeah.
I forgot to ask sir today. Means
Okay,
I
okay.
was reading on that, but I
No,
didn't get
today,
any convincing answer for that. So that's why I didn't give you answer
no,
today.
I have, I don't know actually. That is why I asked you.
Yes.
We will discuss some other time.
Sure, sure. I will,
Okay,
once I get a convincing answer, I will tell you answer for
okay,
that.
okay,
I will
okay.
surely. I remember that question.
Yeah.
It's a good question because
And then see,
actually the understanding of reactive power is not that uh, clear.
yeah.
It's a very
No, I have
difficult.
asked the same
Actually,
question to some other few professors, but what they have told me is that see, for real power, this is real, so that we can analyze. When it comes to reactive power, that is imaginary, so you cannot physically correlate with some physical
no,
things. That is how they.
no, it's not. We can answer that question. Is I can answer that, but I didn't get a good convincing answer. I'm looking
Yeah,
for a
yeah,
good answer for that.
yeah,
I will surely answer that.
yeah, yeah.
There are certain ways to explain these things. And there are one paper also, they have explained reactive power through analogies. Yeah, those analogies are good. I
Okay.
have found some two, three. There is one paper, maybe you can refer that paper.
Can you?
Just a minute, let me just check. But it is, that paper is on reactive power, understanding reactive power, but not reactive power loss. So, but still, you can refer
I
that.
have gone through long back. I have gone through a paper written by some Brazilian journal.
No, it is a paper. It's not a Brazilian. Just let me might be Brazilian. No, no, it's a Indian. This paper is by Indian authors. The paper is the name of the paper is Understanding Reactive Power and its Importance in Power Systems.
Okay.
It's a good. I found it good. Good analogies are there, and few more. One more author. They have
Who is the author, sir?
author is B. Shesh Sai and B. Satya Sai. Okay, so I will surely answer your question whenever I
Okay.
get a good answer.
Yeah.
So think you can see that example, this example 5, and let's stop here for today.
Yes, sir.
Okay, so thank you for joining.
Okay. Thank you, sir. Thank you.
Yeah,
Thank you
we'll
very
meet
much.
next Tuesday.
Next week. Okay.
Thank you.